Thank you very much, and thank you also to everybody who came to my defense, and especially my supervisors, Mr. Moderator, and examiners. So today I'm going to be presenting my thesis topic, Mixed Reality, Multi-User Asymmetric Telecollaboration, and I want to start off with a picture that I think we are all quite familiar with. This is how our typical remote collaboration looks like. We open up Zoom, Teams, or other apps and get a two-dimensional video stream of remote users where most of the cameras have a limited field of view that can constrain how information can be presented, though it works well for face-to-face conversation to some degrees. But it limits us to see others' body language and gaze. Plus, our viewpoint is restricted based on the placement of physical cameras. So if you want to bring the environment as the subject of the conversation, you have to move the camera yourself, which is not engaging, as the users have no control over where they look. And when there are more people or a larger space, it's easier to get lost and feel confused. Some interesting alternatives out there, like 3D video conferencing, Google's Project Starline, which uses high-resolution cameras and depth sensors to create a 3D representation of a person in real time. But the face tracking can only works for one person at a time, and setup is also quite expensive. Then there's the VR option, but the obvious downfall is that you're totally disconnected from the real world's physical space. Then there's a solution like Microsoft Remote Assist that combines the physical and digital worlds, but remote users have limited physical presence and interaction capabilities. Then there are also mixed reality collaborative experiences, which combine both VR and AR, like Microsoft Mesh, which allows collaborators to come together in a shared virtual space. But what I'm interested in is how we can take that shared virtual space and turn it into a collaborative physical space, so remote participants can see the local user space and join in to guide local users. One of the immersive media like 360-degree video, allowing people augmented in virtual reality to experience remote environment from first-person perspective. Prior work has shown some promising results using 360-degree video for inducing various type of presence. It has also been used in remote collaboration. However, there hasn't been a lot of work that addresses multi-user asymmetric collaboration, as they primarily focused on one-to-one and one-to-many. Also, lack of audio-visual sync and multiple viewpoint management. Especially for multi-user collaboration, data size increases the overall latency, which affect the communication and collaboration. Considering that, I formulated my research question. How can multiple remote users effectively connect and collaborate with local users in the mixed reality collaboration space? Then, I broke it down into 5 key aspects. 1. Teleportation. How can multiple remote users achieve a high sense of presence? 2. Representation. How can multiple remote users be effectively represented? 3. Interaction. How can they interact effectively? 4. Viewpoint perspective. How can their viewpoint be managed effectively? 5. Multi-perspective collaboration. How can multi-perspective collaboration be achieved efficiently? To answer these questions, the aim of my dissertation is to develop collaboration tools that enables remote users to teleport and interact with local users and the local users' space in mixed reality environments. That brings me to the contributions of this thesis, which is a research prototype system, MRMAC, which allows multiple remote user in VR to virtually teleport into a real-world task space to collaborate with local users who is in AR. In MRMAC, I presented a design concept for multi-user asymmetric collaboration. My research prototype were able live streaming 4K 360-degree video stream of physical space to multiple remote users. It support face-to-face communication with synchronized audio-visual cues, and multiple avatars and view controls. I have conducted system evaluation with a focus on scalability and latency, along with 2 user studies. In these studies, I explored the impact of user roles and compared MRMAC against 2 baseline conditions. From there, I moved on to the challenges of multiple viewpoint selection, which led to my second contribution, a context-aware viewpoint selection method called Vicarious. In Vicarious, I presented a context-aware viewpoint selection method that simplifies and automates the selection of multiple viewpoints based on user actions and the current context. It also incorporated various visualization and interaction techniques. Then I ran a user study to evaluate the impact of the viewpoint selection method. The results highlighted the need for such system and provided recommendations for design implications. Now I'm going to dive into the system architecture of MR-MAC. Unfortunately, I won't have time to talk about all the implementation details, which are covered in more detail in my thesis. However, I will give a brief high-level overview. I mounted a 360 camera at local user space, and I also take camera feed from AR user headset. Then remote users receive those video feed and also send their viewport stream. I used Web, RTC, SFU architecture and system implemented in Unity 3D game engine. The system provides rich communication and awareness cues for remote users to explore and interact with the local users and their environment, such as view window sharing, multiple avatar control, personalized avatar and spatial audio. Apart from communication cues, a couple of interaction cues were also added, such as 3D spatial pointers and annotation tools. I looked into the latency, especially the end-to-end latency, which broken down by VR and AR users. You will notice that much of it is unavoidable due to camera network latency and encoding and decoding processes. So it was difficult to achieve less than 400 milliseconds due to the inherent latency generated by the devices, but it was adequate for real-time streaming. To understand the efficiency of the system, I looked into its scalability. It was done by simulating an increasing number of VR users with a fixed AR user, and vice versa. The system maintained real-time frame rates. Overall, the network latency was minimal, and the system kept a reasonable frame rate for up to 15 users. I ran a couple of user studies, but I'm going to talk about the second one, which was the most comprehensive. I got a total of 36 participants. It was somewhat uneven between conditions because I conducted the study during the tail end of the pandemic, making it challenging to recruit more participants. The study utilized a 3x2 mixed factorial design with 3 conditions. For the study, I designed a collaborative problem-solving task using Lego and domino bricks, where VR users can see the virtual replica of the model that needs to be built, and AR users have the physical blocks randomly placed on the table. As I mentioned, the study had 3 conditions. The first condition was the usual 2D video streaming, same as Zoom. The second baseline was 360 video streaming without augmented visual cues and kind of like passive viewing experience like YouTube. The last one is MR-MAC. Here is the overall summary of the results obtained from the study. I know there's too much going on and it's hard to track C1, C2, C3. So let's simplify and call it Zoom, 360 video, and MR-MAC. On a side note, I have nothing against Zoom, by the way, it's only for the sake of simplicity. So, spatial presence, which is the sense of being there in the remote space participants, rated MR-MAC higher than other 2 conditions. Social presence, especially the co-presence, which is the sense of being in the remote space with someone, would be significantly higher in MR-MAC. TLX, which indicates how mentally demanding or frustrated the participants felt while performing the task, was quite low in the MR-MAC condition. SUS score was above 68 for MR-MAC, and it was also significantly higher than other 2 conditions, although participants solved the task relatively faster when using MR-MAC, but no significant difference were found. SSQ score was slightly higher in VR between VR pre and post tests than AR pre and post tests, but there was no statistically significant difference. To summarize, I presented a bidirectional asymmetric collaboration system that supports real-time communication, audio-video synchronization, and at the same time seamlessly blend virtual assets into the scene. I've done the system evaluation, which shown reasonable scalability and low latency performance. I also ran user study where participants were able to collaborate and solve the task faster, and overall participants shown preference on MR-MAC over the baselines. Part of this has been accepted and presented at ISMAR. So, why travel with a hefty backpack when you can teleport with MR-MAC? Now, I'll talk about a different problem: managing multiple viewpoints during collaboration. Managing multiple viewpoints can be challenging because users need to decide which views to focus on. For example, if you watch this video one time, it's very hard to comprehend what's going on, so it potentially leads to overlooked information or user actions. One solution is to physically shift or toggle viewpoints, but this consumes time and adds the cognitive load of choosing the right perspective. But if we somehow highlight it or guide user attention, that could potentially help. That was the motivation behind Vicarious. In Vicarious, I presented a context-aware viewpoint selection method that simplifies and automates the selection of multiple viewpoints based on user actions in the current context. It also incorporated various visualization and interaction techniques. So, how I did it. First, from the list of multiple viewpoints, I extracted saliency information and used it as an indication of where the areas of interest are. Then create a saliency map by combining 3 attention cues. It helps in identifying visually prominent content, but it wasn't enough to determine the optimal viewpoint. We also incorporated a set of predefined functionalities or features which users can access through user interfaces. For verbal cues, all users can use voice chat. System identifies the voice activity and calculate intensity. For visual cues, users had pointers, annotations, and gestures that translated through avatar, so system keep track of changes in these user activities on the scene and assign a weight value. In Vicarious, user's viewpoint is displayed as a picture-in-picture window. So I added a few interactions to make it easier for users to navigate, such as 1. Smooth follow, 2. Pinned to fixed location, 3. Spatial indication. So going back to our research question 4, which was how we can manage multiple viewpoint. And to find out, I introduced 4 distinct conditions for viewpoint selection: no selection, manual selection, guided selection, and automatic selection. And going back to research question 5, which was how can multi-perspective collaboration support collaborative tasks. To evaluate that, we asked 2 questions. Would context-aware viewpoint selection increase the sense of presence? Would context-aware viewpoint selection improve the task performance? I ran a user study. This time around, I designed a 4x2 mixed factorial design with 27 participants, and none of them used this application before. First off, we compared various forms of presence that were being induced. For social presence, we did see an increase for users in GS conditions. This means that people were indeed more engaged in the conversation, especially co-presence, which is the sense that you're there with someone, was high in the GS condition. A significant difference is found in the perceived workload in the guided condition. The TLX score was significantly lower in the guided condition than in the other conditions, which wasn't surprising, since guided selection we are doing the work for participants. Now let's look at the task completion time. The first thing we noticed immediately is that people in the guided condition, where the optimal viewpoint was highlighted for them, could complete the task significantly faster than in the other conditions. There wasn't a significant difference between the other conditions. This is also probably not too surprising because they don't have to find the viewpoint by themselves or attempt to select a particular viewpoint. The system highlights it for them. I asked participants which conditions they preferred for various forms of presence, and there was a tendency to prefer guided and automatic selection because people felt more engaged. This was especially noticeable in question 4, which asked about understanding and communicating with partners. Participants perceived the GS conditions as the most effective for understanding and communicating with partners. As for question 5 regarding task completion, participants found both the GS and AS conditions to be most helpful. I didn't really see any differences in the spatial presence of each of the conditions, which is the sense that you're really there inside that shared environment. However, it's worth noting that we didn't have many participants for this aspect. SUS score for guided selection was above average, which is the 68 mark. However, I didn't find a significant difference between conditions, nor did observe any interaction effect. I've also looked into simulator sickness scores, found working in the MS setup resulted in a slight increase in total scores. However, no significant increase in symptoms was reported. Particularly, participants in the GS condition reported experiencing considerably less simulator sickness than others. To summarize, we introduced a context-aware viewpoint selection method that automates the selection between multiple viewpoints. Our optimal viewpoint selection takes visual saliency, user actions, and the current context into account. We ran user evaluations in 4 different conditions, with 2 using our viewpoint selection method to find the optional viewpoint. We found having optimal viewpoint selection improved users' task space, understanding and task performance, and also reduced cognitive load. Overall, GS was the most preferred, performing well across multiple metrics. That tells us users preferred the intervention, but not too much intervention. They didn't like us to do the work for them. So, why work remotely when you can work vicariously? Part of this work has been accepted and presented at VRST conference. In conclusion, through this thesis I shown, rich real-time telepresence experiences can feasibly be created by utilizing MRMAC. MRMAC induces significantly more spatial presence than 2D and 360 video alone. These experiences still pose a significant engineering challenge, and this thesis opened up a lot of future research opportunities, such as incorporating depth into the architecture and exploring more expert-oriented user studies, as pointed out by the examiners. So, as I said, this research is just starting to unfold, presenting numerous opportunities for further exploration. There is still much that can be done. I still have the systematic literature review that we are submitting soon, so I will keep working on that. Thanks so much for your attention.